Good afternoon, everyone. Thank you very much for joining us in this presentation. I am Dr. Gonzalo Latorre Parra, and today I will be presenting our paper, which we title Interpretable Federated Transformer Log Learning for Cloud Threat Forensics. This work was made possible thanks to the support of the Open Cloud Institute and the collective efforts from all the listed authors in this paper. The motivation of our work focuses on three main points. First, we have observed a lack of public datasets that present relevant data collected from modern infrastructures that were compromised by novel attacks. In this aspect, we found that many works make use of syslog datasets collected from distributed systems, which unfortunately hold a low diversity of unique logs. Second, most works focus on building a centralized AI model for log analysis, which requires user data to be shipped to a central server for training a model. While such approaches improve the performance of deep learning models, they also introduce fundamental problems of privacy, ownership, and data locality. Third, while many works present proposals that make use of deep learning models for detection purposes, most of these fail to provide a mechanism that gives insight to the decision-making process derived from the proposed deep learning-based solutions. This is fundamental in the security space to enable cyber threat forensics. Our work presents the following contributions to the scientific community. First, we generate a cyber threat detection dataset consisting of 8.4 million syslogs collected during the second half of 2020 from a production-level environment. The environment hosted 62 instances running uncompromised cloud collaboration services and 17 instances running threat samples. Second, we designed and implemented the first interpretable federated transformer log learning model for threat detection in syslog with the capability of revealing actionable information triggering the model's outcome. Third, we validate our model's performance by training it using two datasets while comparing it against state-of-the-art works. Fourth, we discover a strong correlation between log messages carrying indicators of the executed threat sample and the attention given to the corresponding mapped input sequence, triggering the threat detection. By using our own cloud-based cybersecurity framework for synthetic data generation, we created three end-user environments. During the second half of 2020, 4 simulating a non-malicious environment. We also generated experiments where we executed 17 distinct malicious software samples, each one of them in a separate isolated environment. Overall, we were able to collect 2.2 billion data points consisting of audit logs, structured and unstructured system logs, network data, system metrics, and syslogs generated from the analysis of network traffic. We have published in a GitHub repository the subset of data consisting of 8.4 million syslogs. We have named this subset the Cyber Threat Detection Dataset, or CTDD in short. The publication of this dataset was motivated by the number of works making use of the HDFS dataset to train models for detecting system anomalies using syslogs. Compared to the HDFS dataset, our CTDD dataset presents a great variety of unique log patterns and a more complex relationship between log sequences in the time series. This observation was validated by manually generating strict rules to parse each log in the HDFS dataset, where we discovered a total of 50 different unique log templates. We validated that most log templates in this dataset varied only a few parameter values such as block IDs, IPs, and port numbers. In the Pareto presented in the figure on the right, we can observe that the top 10 templates with the highest count in the HDFS dataset make 99.63% of the data points. We performed a similar study with the logs obtained from the Practicum 2020 cluster and from the 17 environments running malicious samples. Different from the strict rule generation applied in the HDFS dataset, we identified 446 unique log templates using the spell parser. It is important to note that this data subset only represents 31.47% of the CTDD dataset. In the figure on the left, the top 10 log templates with the highest count in the CTDD dataset make 69.2 37% of the data points in this subset. Our proposed framework requires a collaboration of two entities, namely the computing systems hosted in each organization unit and the federated learning server. In our framework, a set of clients contributing to the global federated learning model receive a set of hyperparameters and initial model parameters for training local transformer-based models using their local data. These basically are these business units that I present over here. Each client sends the learned parameters and their computing interpretability weights to the federated learning server. Accordingly, the federated learning server aggregates the learned parameters to generate an updated global federated learning model. Afterwards, the interpretability module at the federated learning server generates the federated interpretability weights. Finally, the federated learning server shares the newly computed weights with all the clients. The experimental results presented in this table require us to train 1,200 individual models in this experiment. We compare the experimental results achieved by our proposed model with those presented by state-of-the-art unsupervised centralized methods, namely log-robust, deep log, log anomaly, and hit anomaly. As state-of-the-art methods use a centralized training approach, we use standard stochastic gradient descent training on the full training dataset with no client partitioning to make the intended comparison. Our first experiment was performed using the NDSS dataset using a centralized learning approach with an F-score of 0.997. Hit anomaly achieved the best performance of all compared models. We attribute this achievement to two main points. First, the larger number of identified event templates, 46 in this case, used by hit anomaly, compared to 29 used by deep log and log robust. Second, the approach taken for learnings from sequences of event templates and parameter values. In the second experiment, we train and test deep log and our proposed model with the CTDD dataset in a centralized learning setting. A drastic performance decrease was observed in both models. This is a direct impact from the increased complexity in the CTDD dataset, as previously discussed. Still, in this case, our proposed model outperformed deep log. The third experiment was conducted with the NDSS dataset using a federated learning approach. We only conducted experiments using a federated learning approach using the proposed model, as the other works we use for comparison focus on a centralized solution. The experiments demonstrate that the proposed model outperforms models built by a central entity for most cases. Moreover, we note that the performance stabilizes as the number of rounds and contributing clients increases. This is a step-by-step example on how our model makes an inference over a sequence of logs abstracted from an NTP amplification DOS attack. In such attack, the attacker exploits publicly accessible NTP protocol servers to overwhelm the target with UDP traffic. The NTP server responds by sending the list to the spoof IP address. In this example, we have a sequence of 13 log templates and the corresponding log keys. Our model takes as an input 10 log keys at a time and predicts the top 3 log key candidates that follow this sequence. Anomalies are identified by comparing the known log key following the input sequence with the given candidates. If no match is found, then we take this observation as an anomaly. If a given number of anomalies is found within a specific time frame, then we consider to have observed a thread in the given sequence. The interpretability module computes the interpretability attention-based weights by aggregating the attention of every unique key observed across all input sequences for each unique ground truth key denoted by epsilon. In this figure, the x-axis represents the unique keys observed across all sequences from all clients, and the y-axis represents the unique ground truth keys observed by all clients. This figure provides a representation on how the attention-based weights are generated in each local model using multi-head attention models. The interpretability attention-based weights can also be computed from syslogs captured from malicious environments. As seen in this figure, we computed the attention-based weights for 3 experiments: NTP DOS attack, SymFlood attack, and BT DOS attack. We present the computed attention-based weights through saliency maps. In the left-hand side, we present the saliency maps from log sequences generated by multiple DOS attacks. The saliency map presented in the bottom right corner shows the federated attention of NTP, DOS, SymFlood, and BT DOS attacks aggregated. The federated learning server aggregates the interpretability attention-based weights provided by each client to generate a federated interpretability attention-based weights, shown over here. This process can be performed with non-malicious and malicious data samples. This is for the non-malicious and this is for the malicious data samples. When comparing the saliency maps from federated non-malicious and federated malicious scenarios, we can distinguish a difference in attention distribution. The picture on the left presents the aggregation of attention-based weights of 2 clients that we presented in our framework. The figure on the right presents the aggregation of the attention-based weights of the 17 malicious samples we use in our experimentation. To measure the attention distribution difference for a specific sample, the interpretability module performs a goodness of fit test of the client's interpretability attention-based weight with respect to a given federated interpretability attention-based weight. 2 cases were built to measure differences. In the first case, we computed the interpretability attention-based weight for each experiment running a malicious software sample. We calculated the chi-square statistic for each of these against the federated interpretability attention-based weight resulting from the aggregation of the interpretability attention-based weights from all malicious scenarios. The chi-square statistic resulting from this case computed to an average of 42.66 and a p-value of 1. The results are shown in the figure at the left. Given these results, we do not reject the hypothesis that the cyber threats share the same distribution as the federated client interpretability attention-based weights of compromised systems. In the second case, we performed the same comparison, but now with respect to the federated client interpretability attention-based weights of uncompromised systems. The chi-square statistic in this second case computed to 66,452 and a p-value of 0. The values from the chi-square statistics for the latter comparison were far greater than the statistics obtained in the first case. The results are shown in this second figure from left to right. Given these results, we reject the hypothesis that the distribution of client interpretability attention-based weights for any cyber threat differs from the distribution of the federated client interpretability attention-based weights of uncompromised systems. The chi-square statistic computed with 448 degrees of freedom is presented in the last figure. Our future work contemplates the expansion of the current model to process NSStream and seek logs for intrusion detection. We are also considering the expansion of our dataset to include seek and NSStream data collected from the new experiments. The following are the references of the related works we mentioned in this presentation. Thank you very much for your time.